Okay, so we are now recording. Take a look at the calendar for this course. And we can see here today is February 21st, so we'll finish up the MNIST classifier in Simple NN, PyTorch Fast AI, and discuss the homework. Next week, my plan is to cover CNN, so we'll start getting into one of the topics. So we've been using the CNN Learner, obviously, but we'll get into some ideas of machine learning, deep learning, and convolutional neural networks. Now, notice here, very important, March 2nd, I have it designated as your midterm exam. So any issues with that, guys?
March 2nd is a Wednesday.
Yeah, does this class meet twice a week?
No. Yeah. Sorry. What that means is it would be on the 28th. I just break up the two, but I know we run on the same day. It would be then February 28th, the second half. So usually the second half of today, I always link here in the calendar. Does that make sense?
So our midterm's like half the class, or is it like a take-home midterm?
Yeah, it'll be electronic. So we'll do it here in this medium. I'll post it on Brightspace. And then you guys will have the 2 hours to solve it, basically. Okay. Or it could be a problem that where I gave you 24 hours. So
Sounds good.
All right. But yeah, so it'll be on February 28th. Okay. So just I thought you guys had noticed that what I do is I take the first half and put it here, and the second half and put it here. But otherwise, it's on the February 28th. Okay, so next week, basically, your midterm exam will take place. All right. All right. Before I get started, are there any questions?
Are we going to talk about the ethics homework at the end, or can we do that now?
What would you prefer?
I don't mind either way.
Yeah, so let's do it. I want to finish the that lecture because once I finish it, we can move on to something else. So let me finish that, and then we can go to the homework. We should have enough time.
Okay.
Right. Anything else? Nope. All right. So let's go ahead then, and let me start the machine. Okay. Let me just start up the connection with the Jupyter Notebook. Okay. Let me navigate to the course. Okay, and the name of this, I think, was Fundamentals, right? I think that's the Jupyter. Okay. All right, I'm going to start the Jupyter Notebook now. Okay. Sorry, this takes me a while to do, but I'm almost there. All right, so that should work. I'm going to share the screen now. And you should be seeing the Jupyter Notebook here, or the Jupyter Notebooks. The one that we were processing the other day was recording. We were processing fundamentals ML MNIST, which is already posted on Brightspace or on GitHub. Okay, so there it is. So I'm not going to go over this code, obviously, because it's taken a while to get through it. But today we should be done with it. Okay, so we went over this. If you remember, we were kind of discussing how to train a model. We trained a quadratic function. We saw that. Saw a little bit of how the learning rate works. And then this is kind of the scenario, right? So this is the scenario where we were. Okay, so we looked at a data set. This data set follows a specific function, which looks like a quadratic with a little bit of noise. So when we looked at the picture, we said, oh, I can build that model. I don't need a neural network. I know it looks like a quadratic, so I'm going to build a quadratic function. And we did that. And then we used that function to predict. And then we trained it by creating this MSE function. And I discussed everything about the gradients and how they work, right? And then we saw in the graph that the function wasn't very good with random values. But then as we started training, updating the gradients with the learning rate, it started to approximate it a little bit better. You saw the optimization go down. And then here we kind of saw that the function started to approximate. The blue function started to, the predicted started to approximate the real function. So now then, once we completed that, we decided, okay, now we're going to use MNIST instead. Okay. To complete this task. So here we got as far. So I think this is where so this is kind of what we were, the piece that we were looking at. So now instead of a quadratic function, we actually want to build a classifier with selected data from MNIST. So we had stack 3s and stack 7s. Right, and we concatenated those, right, and we use a view to kind of change the shape from 2D to 1D. That gave us our train X. Then we calculated the labels. That's just 1s and 0s, right? And so the number of stack 3s that we have, that's the length of 1s, and then the number of 7s that we have, that's the length of 7s of 0s. And so we have our labels and we have our X data. So we completed that. Then we talked about how what unsqueeze does, and we saw that for operations to work correctly, we needed to change the array from this shape to this shape, right? To make it, instead of a row vector, make it into a column vector. So we ended up with 12,396 samples. of size 784, which is the features, and then we have the labels. So we went over that, and then we started looking at creating the data set. Okay. So started to look at getting the data set. So we did PyTorch requires a data set to be a tuple, X and Y. So we did SIP and then list, and then that creates dset. If we want to get just one sample here, then we can take this sample is of size 784 because there's only one sample and it's associated label. We did the same with the validation. So we took the validation 3s and 10s, reshaped it with the view to be of size 784, added the labels, and created the validation data set as well. So that means we have our data there. Okay. So the validation set is done, valid D set. And now what we need to do is we're going to do the training again, right? So we need a function. This time around, the function, we're going to use the universal function approximator, which is this, y equals wx plus b. That's also usually referred to as the function for a line. Okay, so, but we need to figure out the parameters, right? So the parameters are going to be w and b. So we need params, and to learn a weight for every single one of the 784 pixels in the image. Okay, remember that now we have, we have 700, we have images, and each pixel could have a contribution to the prediction. So we need to figure out what that prediction is, or what that contribution is by the weights. So again, we repeat the same process. We initialize the parameters of size, whatever it's going to be. Notice that we randomly initialize the values, and we say that it requires grad. So that's basically where we're telling PyTorch that these are the variables that it needs to calculate gradients for. Basically to do the calculus part, okay? Okay, so requires grad, then we do weights, initialize weights and bias by using the init params function. This is of size 784 by 1, and this is of size 1, as we discussed last week. And then now we have basically the weights, so we can, or the parameters, so we can go ahead and predict the value for one image using random parameters. So that's basically where we are, and we predict some value here, whatever it is. And this might be different for you guys. Now, if we want, now this only does the work for one image, right? So for one image, so if we want to do this in a more generic function that does it for a data set, let's say we provide the entire test set in here, then we can create the function linear. So we can do define linear xb, and it's going to be xb the inputs times the weights plus the bias, and it should give us a value, linear preds. So you can see when we run preds, we get this. And that's basically where we stopped on last week. So we can now pick up here and continue. Okay, so we have pretty much some good things. We have the equations and the parameters, and we have the data. So let me just run this and make sure everything is running correctly. Let me start. clear the output here. Okay, and then I'm gonna run it one by one. Just to make sure everything is updated. Huh. Mean loss is not defined. This was working before, wasn't it? Where's this error coming from? Well, this is.
If you go to kernel and then restart and run all, it'll run the whole thing.
Yeah, I
That
did.
might help you.
Yeah, because there should be no errors with this. This is just the code that we had from last Monday, and everything worked. See, it keeps saying that it doesn't know that loss function. Loss. Give me a sec. Loss is MSE. Okay, let me just.
Just a possibility.
Yeah.
It's that loss. Why real is that supposed to be there? Because when I look in mine, right at that spot, I have the fastbook import like you do, then the definition and then the plot function, but I don't have the loss. Why? I don't know if mine's wrong or not.
Why did I put that there?
It might have accidentally got copy and pasted there or something.
Yeah.
Am I the only one without that there?
No, you're right. I just found it. I just don't know why. Huh.
Or maybe it was commented out.
Yeah. Let's see. Actually, I want to make sure this is all correct. So let's see. Clear output. So libraries. Print. Data. Print. Print. Print in gradient form. Print lengths. Show image. Stacking the data. Print. Show images. Okay. Prints the values. Prints a couple of tensors. Okay, the validation set. shapes. And then distance type thing. Histories. Times that. This. So this is where the error was happening from fast book. Which graph is that? The optimization one. Yeah, so from fast book, I must have been talking about something and I just added that in there. So yeah, so the library is there. And then the function, right? W2, plot the function. Okay. Then we've got the function, X and Y gradient. Okay. Then the backward propagation, backprop. This part. Then we did the other scenario that we talked about, quadratic. Okay. Right, the training, the optimization, visualization of the optimization. And then this is basically what I was talking about now. So we concatenate the data. We create a data set, PyTorch. Then we do the validation set, so that worked. And then we need the parameters and initialize them and predict something. And then finally we create a function for perfect. All right, for predicting values for the train set. So we're back kind of where we need to be. Okay. So now all right, so this function is, as I said, it's a way xb times weights plus bias. It's a way to give it a data set. So you can see here when we called it linear, basically, because it's really just a linear function. You know, it's actually the function for a line, right? So x times w plus b is the line function. And then we call it here linear with the train set, and then these are the predictions. However, look at those values. Those values are not really that great, right? They don't, you know, they're 17, 15, 28. In our data set, this is what it's predicting. Look at the values it's predicting, 28, 23, 17, 20. In our labeled data set, our values are 1 and 0. We only need to predict 1 and 0, right? Nothing else. So we need a way to modify these values so that the prediction, instead of being 20, it's going to be a value between 0 and 1, for instance, right? And that's called usually an activation function, which is going to transform our linear behavior into some other kind of behavior, some other kind of function. All right, so that's one of the things that we're going to look at today. So we're going to need, assuming that we now know that the values are going to be between 0 and 1, which they are not currently, they are not. We need a way, we still, you know, once values are in range 0 to 1, then we need a way to say, you know, which one is 1 and which one is 0. So what's one good way of doing that? The easiest way, you know, use a threshold. Use 0.5 threshold. This is not optimal. This is just one approach, right? So what that means is we're going to use a cutoff and say values above 0.5 are 1, values below 0.5 are 0. We use this actually in the digital age, right? Everything is voltage is above this or below that, but the voltages are actually a little bit variable. They're not exactly to the number. So we're going to create this function. We can call it corrects, for instance. And this function is preds greater than some value. So currently, it would be 0.5 if we had mapped it, but we haven't mapped it yet, right? The values, in fact, are like this. So we're just going to say anything between positive or negative. So in that case, positive or negative is actually 0. Oops. So we're going to just try that. I'm just playing with things right now, right? That's all I'm doing. So playing with things to see the behavior of it. But I'm trying to show you that we want to predict value 0s and 1s. We're currently predicting 20, 28. So we need to figure this out. So once we've selected all the preds that are greater than 0, we're going to compare those to the train set to see which ones are true, how many are true, and then we can calculate some kind of a mean. So here I'm going to do train y, right? That's correct. And then we can print it, right? So print so this array takes all the values, an array of size n, compares it to that 0, and then returns marked as 1, the ones that meet the condition of, and then that new gets compared with the train y, and we should be able to know the correct prediction. So I'm going to do here print corrects just to take a look. Print corrects. I'm also going to do print length of corrects. And I'm going to print length of train y. Okay, so I'm going to run these. Okay, you can see they're both the same size, so you can compare train y to corrects. So that just gives you the values, and then you can see there's trues and false in there. All right, so now we know which ones match and which ones didn't. And then we can take the mean out of these because trues are like a 1 and false are like a 0, so we can just average that. So then that's going to be R equal corrects dot float dot mean, and then we just want to get the final value, so dot item. Okay, so if I run this one, did I forget to print? Yeah, sorry about that. And there it is. So accuracy is about 49% in this example. So not great, but it's just, I'm just trying some things here. All right, so now whenever, as we learned last week, right, whenever we're training a model, we need to have a loss function. So in the previous example, the loss function was, if you go back to those videos, what was the loss function in the previous examples? You guys remember? No, no one remembers. It was the MSE, right? The mean squared error. So we defined it as MSE, the mean squared error. This is the standard thing that you've learned in linear regression. Predictions, the difference between predictions and targets, square it, get the mean of it, right? That's MSE. However, that's for a different kind of problem. When you're dealing with problems that you have a value of 0 or 1, you need, this is basically a different type of problem, okay? And so we need another loss function. So we need a different loss function. And usually the function used here is called CrossEntropy. In our case, the binary CrossEntropy. So I'll discuss the binary CrossEntropy function today. However, just be aware that PyTorch actually has a nice little function. PyTorch has a function called Torchware. So I'm going to put it in double quotes. It's called torch.where. And this function was very perplexing to me when I first saw it. I'm like, why on earth are they doing this? But it kind of makes sense, I guess, because the problem with the CrossEntropy function is that it's very, what's the word? Not difficult, but just like confusing, I think. It's probably what it is. So a lot of people, I think, may have a hard time understanding CrossEntropy function. I know it took me years to kind of get the feel for how it works. And I think the torch.where function is actually another way of saying the same thing in a more heuristic way, which I thought was interesting. Now, remember, for us to be able to use CrossEntropy or torch.where, we need to have the labels be 0s and 1s. And we need, well, they are, but we need the model to predict 0s and 1s. Currently, our model, this linear function over here, only predicts these values over here. You see, this is why this was important for me to print out, because I wanted you guys to visualize that we don't actually have a function yet that gives us 0s and 1s, or something approximate within the range of 0 and 1 at least, that we could use a threshold or a cutoff similar to the one we use here. Okay, so I'm introducing then two things, two functions. One function that does the loss, no longer MSE. So make a note of this, because I like to ask this question on the exam. Loss is no longer MSE. It is now CrossEntropy. Okay. All right. And also, I forgot to put my tablet here. Give me a second. I'm going to need the tablet for this part. I always spend a lot of time on this function because, in my opinion, it is an extremely fundamental concept. You will always use a loss function in machine learning and deep learning. And as it turns out, CrossEntropy is used. So this one that I'm going to be discussing is the one that you will, you can always use CrossEntropy, basically, is the way that I would put it. So I should be all set. So again, we are setting up here this idea, right? So we have a function, we have data, of course. Don't lose sight of this. We have this function, linear, given an X test, for instance, we've learned some weights and bias. It predicts these values, but these values are not in the range of 0 and 1. We need to change that. Once they are in the range of 0 and 1, then we need a function such as the CrossEntropy. Okay, but also you'll see me PyTorch has this function, Torchware, which is the same behavior. Okay, so let's see. So let me think. I guess I can introduce them however I want. So let's see. Let's start with Torchware, I guess. All right, so I'll start there. So this is going to be my loss function, right? So like I said, my new loss function will be CrossEntropy. But for this problem, because I'm doing MNIST, I'm keeping things kind of general. So let's just call it MNIST loss. Let's just call it that. All right, and MNIST loss actually is, let me make sure I'm recording. Okay. MNIST loss, this function here, is just like any other loss function. So it's going to take the predictions and the true values. So let's call it predictions, comma, and then targets or labels or true, however you want to call it. Okay. And now it basically returns, and this is where we call the function. Okay. So the function is torch.where. Okay. And then we just have to plug in some values. We're going to say that the targets equal 1, comma, 1 minus predictions, comma, predictions, and then we just get the mean of it so that we know we have a value for the loss function. Usually that little value that gets printed out. Okay, so now I need to explain this. In detail. Okay, so let's just write over here that, you know, a description for the torch function, I guess, the best way to do it. So the torch.where function, the torch.where function, which takes, by the way, 3 parameters, as you saw me in there, A, comma, B, comma, C. The Torchware function measures how distant, and this really, we got to go slow with this to really unpack it because it's kind of important. Okay, so the function measures how distant, and you guys can read this, correct? Not too small.
Yeah, we can see it.
So function measures how distant each prediction is from 1. Now notice, this is important. So the function measures how distant each prediction is from 1 if it should be 1. Okay? And how distant it is from 0 and how distant it is from 0 if it should be 0. And then it will take the mean. It will take the mean of all those distances. Okay, that is, if I read this description, and you tell me this is Torchware, and I know it's in reference to the loss function, I will say, well, that's just a cross-entropy function. So why are, but I get it. So we'll discuss the cross-entropy function in a sec, but basically this function measures how distant each prediction is from 1 if it should be 1, and how distant it is from 0 if it should be 0. And then it will take the mean of all those distances. Okay? So that's basically the Torchware function. So what does that mean? So again, we have to go back to, let me run it. Okay. We have to go back to this idea here. We're not actually predicting zeros and ones. We're predicting that range, but our labels are zeros and ones. Therefore, we need a function to map these values to 0 and 1. I will do that in a second with a function called the sigmoid, which is also the way that neural nets become non-linear functions. So you've always said that neural networks are non-linear functions. Logistic regression is a linear function. What that means is, yes, this is a linear function because this is the line, right? This is a line, basically. But a non-linearity would be to take this value and have it produce different numbers that are no longer linear, but that have another kind of shape. So for instance, forcing them to fall within a range of 0 and 1 with some function, right? So that is the thing in deep learning that makes a linear model into a non-linear model. And we'll talk a little bit about the intuition about that as well in a sec. But anyway, so let's finish up the torch.where function. So the torchware, as it says, function measures how distant each prediction is from 1 if it should be 1, and how distant it is from 0 if it should be 0. And then it will take the mean of all those distances. All right, so now I have to switch over to the whiteboard, okay, here. And I'm going to write out, hold on, give me a sec. Right, so if I have here, so here we are. So if you remember that rule that we had before in Torchware, right, that function measures how distant each prediction is from 1 if it should be 1, and how distant it is from 0 if it should be 0, and then it takes the mean of all those distances. So that's equivalent to writing something like this. So we have a cost function, J, and you guys should be seeing the whiteboard.
Yeah.
So we have a cost function, J, given our prediction, right, our model, which is W, X, and Y, right? So the predicted and the real. This is the predicted because that's the function. This is the real, okay? So these are the parameters that go in here, except that this WX is also run through a function, okay? So remember, it's linear like this, and I took out the B just to simplify things. But this is linear. We need to make it non-linear. Okay, and that's why I added the G. So maybe, you know what I'm going to do? I'm going to write this in another color. So this is J, like that. All right, it takes two parameters, the real and the predicted. But the predicted as it's run through this function G, which provides, and we're just going to call it as the sigmoid function. So now the values are definitely in the range 0 and 1. Okay. And then once we have that, we want to say that thing that where says, right? That thing that where says basically says that, you know, function measures how distant each prediction is from 1 if it should be a 1. So we're saying if it's 1 or if it's 0, right? So if it's 1, so if 1, we need to capture that behavior. And that behavior is captured by a function which is minus log of the G Wx like that, okay? So that's basically that function. And the other one is if it's y equals 0, then that is captured by a function minus log 1 minus G Wx, and there's parentheses there. This is exactly the same thing as the where function. So function measures how distant each prediction is from 1 if it should be a 1, this one. Function measures how distant it is from 0 when it should be a 0, this one, okay? Now the intuition of this is the following, and I think with the graph, it'll become very obvious, hopefully. We actually have two if statements, right? We have the case where y is equal to 1 and the case where y is equal to 0. So we said that it's got different this. So what I want, when you see something like this, think of it as that. What was that? What did that function look like? Do you guys agree that this function looks like this in a chart? Guys?
Yes.
Perfect. So then, and you also agree that the sign of something looks like that, correct? So functions have appearances, shapes, right? The sigmoid, which I will draw in a second, looks like an S, a type of an S. That's the sigmoid. Well, just like all of these, this one here, this log, has also a shape, and that shape is the one that captures that whole idea of the torch.where. So now we're gonna go over here and plot these graphs, and then hopefully it'll become obvious. So for the case of, and then we have here this and then this. So this Gx, Gwx, we can just write it as H0. And so the other one then would be 1 minus Gwx can be written as 1 minus H0. Just to simplify it a little bit, okay, if we do that, then over here we can say 1 minus H0, and let's say of x, and then this one is just H0 of x. So now we can plot the graph over here, and you will see that it's exactly what the torch.where function does. But what is really important is for you not to lose sight that this is entropy. Cross entropy, the main loss function in DL. And this is for a lot of the algorithms going forward. So that's why I spend a little bit of time on this one over here. So what do these shapes, if you graph these functions, because they're independent, what do they look like? Well, they look like the following. So this one looks like this, and then this one looks like this. Okay, so this is the cost. Remember, these are cost functions. So this is the penalty. We are trying to minimize the penalty. And then the range here is from 0 to 1, and the range here is from 0 to 1. So what does it say? So before we had established that function measures how distant each prediction is from 1 if it should be 1. Okay, so if it should be 1, what we're saying is the cost should be, if it should be a 1, when we predict a 1, the cost should be low, right? And you can see that here. See how this is the cost, right? So if it should be a 1 and it predicts a 0, is the cost high or low?
High.
High, perfect. If it should be a 1 and it predicts 1, what's the cost?
Low.
Low. You see that? That's exactly the same thing as the Torchware, the same idea, right? So this cost function forces the model, right? In the case when you're looking at a label that should be 1, it forces it to learn towards 1, because otherwise you're going to get high losses, and you never want high losses, you want low losses. So then you're going to say, no, these weights are pretty bad because it's a 1 and I'm predicting zeros and the loss is too high. But if it's a 1 and I'm predicting 1s, the cost function is low, so good, I'm doing good. The other scenario is when y is 0, right? So in the case of y is 0, it means that the label, the true label is 0. So what should the model do? The model should predict zeros, right? And you can see that this function captures that exactly, right? Because when you should be y 0 and it predicts 0, what's the cost, high or low?
Oh,
Oh, perfect. And then finally, then, if it should be 0 and it predicts 1, the cost is high. You see that? And that's cross-entropy. That's how it works. This is obviously just cross-entropy for the binary case. There is a cross-entropy for the multi-class problem. And then finally, what you do is to represent the loss function, because this is kind of like two things, but you can group together the two functions into one. And so the function finally will look something like j equal, and let's just, I'm gonna simplify the terms here, and I'm just gonna say y log of h theta x plus 1 minus y of log 1 minus h theta x, like that. That's basically this one over here, but rewritten in a function, just like before we had in MSE, right? In MSE we had something like y minus y hat squared and all that stuff, right? And that was the function, very intuitive for the linear regression case. Here for the logistic regression case, we have this example of the function like this. And think about it, it does work, right? So for instance, we're looking at the case where y equal 1. The label, the true label should be 1, okay? So what's the function for true label? The function for true label is just that, okay? That's the function for when it's 1, so just log. The other one is not considered. So then if you think about it, when you plug in 1 here, this term is valid, but when you plug in 1 here, 1 minus 1 is 0, so this one goes away. Do you see that, guys? So you only focus on this, which basically means you only focus on this function and you only optimize towards the goal that the value predicted should be a 1. If we look at the other case, if this should be a 0, then what happens? This is a 0, so all of this becomes 0. And so it goes away. And then this one is 1 minus 0, which is 1. So we only focus on this side of it. So that 1 minus h then becomes this one over here, right? So it's 0. We want to minimize that this should be 0. Okay? And so that's, in essence, the cross-entropy function. This is, as I said, only for binary cases, not for multi what is called, I guess, the binary and multi-class form, basically. Is that clear for everyone? Do you guys understand, or do you have any questions about these ideas? No questions? All right, so that then is the cost function. This is kind of simplified by just using the torch.where. Torchware captures the same. If you look, the target where ABC functions measures how distant each prediction is from 1, if it should be 1, and how distant it is from 0, if it should be 0, and then it will take the mean of all those. So at the end of the day, to minimize the mean, right, you should select the values correctly. All right, so that's what we're going to use for CrossEntropy. Not hearing any questions. And as I said, CrossEntropy is very fundamental to deep learning. All right, but the problem we still have is that the data still looks like this, right? The data is still these values over here. And we need it to be in the range from 0 to 1. So basically our data is still linear. We need to make it nonlinear. And so for that, we're going to use the sigmoid function. So the sigmoid make predictions between 0 and 1. So values are going to be converted from these infinite set of numbers to just a range between 0 and 1, which could be infinite. All right, so we need that function. So that's what I'm going to define now. So the sigmoid. So sigmoid function takes in a value x, and it's going to map it to the range between 0 and 1. So return, this is just the math of it. So 1 divided by 1 plus torch exponential negative x. So that's the formula of the sigmoid. There's also, if we don't want to write out the equation, which is actually more recommended, you can use torch.sigmoid. Go ahead, Wyatt.
So torch.exp to the negative x, is that e to the negative x?
That is e to the x. That is correct, sir.
Okay.
Good one. Okay. Yes. So we can actually view it. So let's go ahead and view this one. So hopefully that'll make it a little bit more clear. Let's do to view it. All right, so to view it, we are going to do plot function and here we just plot the torch.sigmoid. Notice I'm just using the sigmoid function here, comma, this is just the title of the chart, sigmoid. And a range, so min equal, let's say -4 to max of +4. Right, and if we run this, it should give us, there it is. That's the sigmoid function. If you notice, all values, regardless of what the input is, right, what the input is on the x-axis, they're always going to map to a range between 0 and 1 on the y-axis. Okay, so that allows us, that's just, algebra, and that allows us to, now we no longer have the problem that our values look like this, because our values will now look like, values from 0 and 1, and now this will work too, okay? The cross-entropy function. So that's fundamental to that idea. So now we can go ahead and update our mness loss function. So initially we had created an mness loss function somewhere in here. Yeah, here, the torch.where function, because the values are still in the broad range, we need to change that. So I'm going to go ahead here. I'm just going to say update mness loss with the sigmoid. And this, the way that PyTorch does it, it's a little bit different from the way that I've always done it in TensorFlow. So I almost feel like you have to, well, this won't be a problem later, I guess, when we actually start using like the neural nets API. But here it's kind of like a after the fact approach, but because we have to do it a couple of times. But anyway, so here we're going to redefine mness loss. So mness loss takes in predictions, comma, targets. And then now I'm going to just copy this one. But the values, the predictions need to be mapped to the 0 and 1. So now I'm going to say predictions equal predictions, and conveniently Torch provides the object, a Torch object can just have a method called sigmoid. So it's very convenient in that sense. Or we could run it through a function, and that should also work. All right, and that's it, right? So hopefully that is one of the big concepts that I wanted to discuss today with regards to, this lecture basically was a lot about cross-entropy. So last week we talked about optimization and the learning rate in general, but we were using just simplified functions and MSE. Today, because we are now making the jump from data that looks like this to data in the range of 0s and 1s. So we need another type of loss function. So we introduced a sigmoid, and we introduced a cross-entropy function, which, as I said, is this one, right? So this representation over here, or that representation, you want to see it like that. So just be aware, but torch.where take care of that logic pretty much. So now we can go back to the Jupyter notebook, and that's basically two very important concepts that I'm going to say that I wanted to discuss for today. Does this make sense, guys? Yeah. All right. So now what we're going to do is we're done basically today with kind of now the theory. All right. So today that was really I'm going to label this video cross-entropy and sigmoid probably for machine learning probably. And now we're ready to just put it all together. Okay, so all these ideas, everything that we talked about for a while, now we are ready to just put it all together because we have that function done. So now let's call this section actually putting it all for mness, right? Remember, we're trying to predict for mness. So now I'm just going to copy, I'm going to write, because this is all like scattered all over the place, spaghetti kind of thing. So I want you to just have one script that has all of it together. So this cell will basically just be copying a lot of these things. So let's start with the train set, right? So let's find the train set. So it was this one, right? So I'm going to copy this. And this one too, and the validation. So I'm just going to copy those, but now all of it just in one single script. Okay, and then we're going to clean it up a little. Okay, so I copied that one. I need this one. And the validation. Okay, and the validation also, which is this one. Okay. So let's just go over it. Let's see, we create the train X torch cat concatenation of stack 3s, stack 7s. We do the view. Okay. We can get rid of this just to make it more succinct and clean. Train Y is going to be the tensor of 1s, length 3s, plus 0s, length 7s, and the unsqueezed version. Actually. So, unsqueeze, right? Get rid of that. And then we're going to create a data set. So I'm going to get rid of this. So that's going to be data set of, and then remember that PyTorch needs them to be tuples. So train X, train Y, we create D set. That's it. That's our train set. Then we do the validation set over here. And that should be kind of the same. Validation X is torch cat, valid 3s, 10s, valid 7, 10s. This is just the way we called it initially, if you remember. View, that's correct. 784 or 28 by 28, however you want to do it, same. Valid Y is tensor 1s, length, valid 3s, 0s, valid, and then on squeeze. And then the valid D set is going to be listing and sipping valid X, valid Y for the data. All right, so that's, I just copied it, but I'm putting it all together as one script. So that's our data. Then we're going to create in a very much in a fast AI way, in a fast AI way. Remember that here we're using PyTorch, and sometimes we use just fast AI's own built-in things. So we're going to use the data loader function, data loader, and data loader will take D set. So this is for the training, but when we start grabbing data to train our model, because we might want to use GPUs, etc., as I am using my GPU box, I need to specify the size of the batches, right? And I can just do that conveniently in here. So I can just say batch size, batch size, and just select the size, so 256, something like that. Okay. If this is too big for your own machines, you can make it smaller. Try that. Just make it multiples of 32, 64, that kind of thing. And then we're going to do the same for the validation. So I'm going to do valid underscore DL. Again, I'm going to call data loader. This one is going to take valid D set, comma, and the batch size can be the same. So I'm going to do batch size equal 256. Okay, so now I have my data there in data loaders format. So we have the data loaders done. The next function is to create the init parameters. I'm going to add a line here maybe. So we define init params, right? The same function we had before. Oh, actually, we can just copy this. So let's look for it. Init params. Here it is, right? So it's basically this code, right? So we need init params, weights, and params. So roughly speaking, these. We'll copy. Just like that. So we look, let's just double check. So init params size, so, and then it initializes our weights and biases to random values within with some dimensions and some values in them based on this, right? Kind of a random thing with a value. And we say, very importantly, remember, requires grad. Remember that the weights and the biases are the thing we're trying to learn. So the thing we are trying to learn is the thing that requires grad. It's the thing that's going to require the gradients, which are the derivatives, as we discussed in previous lecture, the calculus of what's going on, right? And we've gone over that idea already, so I don't have to repeat it. And then we're going to initialize the actual weights and the biases. So that's going to be weights, init params, 28 by 28 by 1, yeah. And then the biases, init params, 1. And then also, more conveniently, we can create an object params, which has weights and bias. So, you can treat it as a tuple, and it's a way that we can access both of them together very conveniently. This is really nice, actually. Okay. Once we are done with that one, we can go ahead and define our linear function, okay, which we can also copy, which was, for now, we're just going to use this one. But as you can see, we're more and more modifying things. So we have that. So define linear, it takes some data now. And basically it's linear here. So the data times the weights plus the bias. And that's our prediction function. Okay. All right. Then we need the loss function, which is what is the major topic today, using those two functions I introduced. So where was this one, right? Okay, so the MNIST loss is predictions target. It's going to have the predictions running through the sigmoid, remember, and then the Torchware, which is the CrossEntropy idea that I discussed. Okay, and so that's basically all of it. And now what remains is for us to do the training and the testing. Okay, so the next step that we need to define is we need, a way of training. So I'm going to just jump ahead here. Machine learning, deep learning usually has what is called the main loop. So I've always called this the main loop, at least myself, the main loop. And this is where we're going to do the training. We need to specify the learning rate. I recommend that you guys play with this learning rate. Try different values here. And see the results, okay? But that's the learning rate, the best work for me. I think actually Jason had showed some function to calculate an optimal learning rate, which was very interesting. But here I just plugged it in. We have a for loop. So for I in range, so that means the number of epochs. So the number of epochs here is going to be $20. So it basically means we look at the data 20 times. The same data, we're going to look at it 20 times, but usually you would want to randomize it a little bit every time. And epochs. Okay, and this is the main loop. So in the main loop, we need to do something, right? So we need to train and test, basically. So we need to train and test. Okay, so that's what we're going to do in the second half of today. So if you look at the time, it is currently 3:50. So we started at 2:30, so 2:30 to 3:30 to 3:50, right? So we're going to take a 10-minute break from 3:50 to 4 o'clock. And then at 4, we will start, and we should be able to conclude this today and have enough time to work on the homework assignment. Does that sound good?
Yep.
So I'm going to save this. Let's take a 10-minute break, stop the recording.